Hello, welcome to my presentation video on the basics of harmonics. My name is Martin Lavachka, and in this video I will talk about harmonics, their effects on electrical installations, and how to mitigate them. We define harmonics as current and voltage that are distorted and deviate from sinusoidal waveforms. Harmonic currents are caused by nonlinear loads connected to the distribution system. Voltage harmonics are caused by the flow of harmonic currents through the system impedances that distort the supply voltage. The harmonic of order h in a signal is the sinusoidal component with a frequency h times the fundamental frequency. By looking at the image, you can see the fundamental frequency, which is 50 Hz. You can also hear about the fundamental frequency as the first order harmonic. The third order harmonic has a frequency of 150 Hz. The fifth order harmonic has a frequency of 250 Hz, etc. Above the fundamental frequency, there is a current wave affected by harmonic distortion in a 50 Hz electrical distribution system. This distorted signal is the sum of a series of superimposed harmonics. Harmonic currents are generated by the nonlinear loads of the installation. A load is said to be nonlinear when the current it consumes does not have the same waveform as the supply voltage. Typical nonlinear loads are welding machines, arc and induction furnaces, battery chargers, speed drivers, UPS, office equipment such as PCs, printers, servers, and home appliances such as televisions, microwave ovens, and light dimmers. For a given harmonic current caused by the nonlinear load, the voltage distortion is proportional to the impedance in the distribution network. The reactance of a conductor increases as a function of the frequency of the current flowing through the conductor. For each harmonic order, there is an impedance in the supply circuit. When harmonic current flows through the impedance, it creates a harmonic voltage. As a result, the voltage at the point B is distorted. All devices supplied through point B receive a distorted voltage. Nonlinear loads inject harmonic currents upstream of the distribution network towards the source. The harmonic currents generated by the different loads sum up at the busbar level, creating harmonic distortion. Due to different load technologies, harmonic currents of the same order are generally not in phase. This diversity effect results in a partial sum. THDU is an indicator of voltage wave distortion. If the value is less than or equal to 5%, it's okay and there is no risk of malfunction. If the value is between 5 and 8%, there is a significant harmonic distortion in the network and some malfunctions may occur. If the value is equal to or greater than 8%, significant harmonic distortion exists and malfunctions are likely to occur. An in-depth analysis of the installation and mitigation devices is required. THDI is an indicator of current wave distortion. Current distortion can be different in different parts of the installation. The origin of possible disturbances can be detected by measuring the THDI of different circuits. If the value is less than or equal to 10%, it is okay and there is no risk of malfunction. If the value is between 10 and 50%, there is significant harmonic distortion with the risk of temperature rise, resulting in the need to oversize cables and sources. If the value is equal to or greater than 50%, significant harmonic distortion exists and malfunctions are likely. In-depth analysis of the installation and mitigation devices is required. The most significant harmonic orders in three-phase distribution networks are the odd orders. Utilities focus primarily on the lower harmonic orders up to 13. In general, harmonic conditioning of orders up to 13 is sufficient. More comprehensive conditioning takes into account harmonic orders up to 25. Sufficiently accurate measurements are obtained by measuring harmonics up to the 30th order. The five main effects of harmonics in electric installations are resonance, in case that capacitor bank is implemented, increased losses in conductors, asynchronous machines and capacitors, overload of generators, UPS, transformers, asynchronous machines, capacitors and neutral conductors, disturbances that affect sensitive loads and economic losses due to energy losses, higher subscription cost, oversizing and reduction in the useful life of equipment, and noisy and stripping and shutdowns of facilities. We will go through several slides that explain the effects of harmonics on specific equipment in the installation. I'll let each slide for 5 seconds and move on to the next one without leaving any comments. So if you want to read it, you can pause the video. Once you finish reading, you can continue watching the video. There are three different types of solutions to attenuate harmonics. The first solution is modifications to the installation. The second solution is to implement special devices in the supply system. And the third is harmonic filtering. To limit the propagation of harmonics in the distribution network, Different solutions must be taken into account, especially when designing a new installation. The first possible modification in the installation is to position the nonlinear loads upstream of the system. As the short circuit power decreases, the overall harmonic disturbances increase. All economic consideration aside, it is preferable to connect nonlinear loads as far upstream as possible. The second possible modification in the installation is to group the nonlinear loads. Nonlinear devices must be separate from others. The two groups of devices must be supplied by different sets of bus bars. The third possible modification to the installation is to create separate sources. When attempting to limit harmonics, further improvement can be obtained by creating a source through a separate transformer. The disadvantage is the increased cost of installation. Having a suitable system earthing arrangement is also important to manage harmonics. In the TNC system, a single conductor pen protects in case of earth faults and unbalanced current flow. Under steady-state conditions, harmonic currents flow in the pen. Due to the impedance of the pen, this results in slight potential differences between devices that can cause electronic equipment to malfunction. Therefore, the TNC system should be reserved for supplying power circuits at the head of the installation and should not be used to supply sensitive loads. The TNS system is recommended if harmonics are present. The neutral conductor and the PE protective conductor are completely separate, and therefore the potential throughout the distribution network is more uniform. Another solution may be the installation of transformers with special connections. Different transformer connections can eliminate certain harmonic orders in the upstream network. When variable speed drives are supplied, it is possible to smooth the current by installing line reactors. By increasing the impedance of the supply circuit, the harmonic current is limited. In cases where the preventive action presented so far is insufficient, it is necessary to implement harmonic filtering systems in the installation. There are three types of harmonic filters: passive, active, and hybrid. Passive filters offer power, power factor correction and high current filtering capabilities. It also reduces harmonic voltages in installations where the supply voltage is disturbed. If the level of reactive power supply is high, it is recommended to turn off the passive filter at times when the load percentage is low. Preliminary studies for a filter should take into account the possible presence of power factor correction capacitor banks that may have to be removed. Typical applications of passive filters are industrial installations with a set of nonlinear loads that represent more than 500 kVA, such as variable speed drivers, UPS, rectifiers, etc. Installations that require power factor correction, installations where voltage distortion must be reduced to avoid disturbing sensitive loads, and installation where current distortion must be reduced to avoid overloads. The passive filter is installed in parallel with the nonlinear load. This bypass circuit absorbs harmonics, thus preventing their flow into the distribution network. Generally speaking, the passive filter is tuned to a harmonic order close to the order to be removed. Multiple filter branches connected in parallel can be used if a significant reduction in distortion of various harmonic orders is required. Active filters filter out harmonics over a wide range of frequencies and can be adapted to any type of load. On the other hand, the power ratings are limited. Typical applications are commercial installations with a set of nonlinear loads representing less than 500 kVA, and installations where current distortion must be reduced to avoid overloads. The parallel connected active harmonic conditioner compensates the harmonic current. The active filter injects the harmonics consumed by the nonlinear load in the opposite phase so that the line current remains sinusoidal. Hybrid filters combine the performance of active and passive filters. This new filtering solution offers the advantages of both types of filters and covers a wide range of power and performance levels. We come to the end of this presentation. Now you know the basics of harmonics and how to mitigate them. Thanks so much for watching. Stay tuned for the next video where I will talk about the effects of harmonics on capacitors and neutral conductors.